Hi everyone, and welcome to NDC 2020. Today I'm going to talk to you about building rock solid serverless applications. My name is William Liebenberg. I'm a solution architect at SSW. You can find me on Twitter. I've got a website called azuregems.io, so you can find some cool tips about Azure. You can find me on LinkedIn, so if you want to engage a bit more formally. And just a bit of my background, I started programming when I was about 5 years old. Wrote my first program on a Spectre Video 328. It's a big, clunky, beige-looking thing like this, and it had a whole 8K of memory. Everything else after that had to be loaded from cassette tapes. They hardly ever exist anymore. So long before the internet and CD-ROMs and all that kind of stuff. So everything was pretty basic back then. And then, years later, I started developing professionally in 2004. But this was when IDEs were pretty much low res compared to these days. But still, we felt like we could rule the world with source code. Eventually, I moved over to .NET version 2. Skipped version 1 because I thought, oh, what's this crazy new technology? It's not going to last. But hey, happy to say I was wrong. We've got .NET 5 these days. It's been with us for so long, and it is fantastic. I spent many years in the 3D industrial training industry, virtual reality, and I was lucky enough to get one of the very first Oculus Rift dev kits in Australia to help train people in their jobs to work safely so they don't hurt anyone else or themselves. Then I fell in love with Azure in about 2014, so about 6 years ago. Not a day goes by that I don't use Azure. It's so big, there's something for everyone. And today we're going to have a look at a small slice of Azure. So I'm going to start off by looking at what is clean code and the solid principles. And then how do we apply that to building or in architecting our serverless applications? Then I want to sort of go and see what can we do to harden our applications, add some resiliency, and make sure then they can perform, scale efficiently. And so let's get started with clean code. So why bother with clean code? Well, I'm sure we've all been in this scenario. We do our sprint reviews or code reviews, and we measure the quality of code. There's a standard measure, the WTFs per minute. So solid principles help us sort of to either make sure we have this very low rate of WTFs per minute. Now, on one end, you'll have the devs that sort of come in, they're duct tape coders. They just quickly fix it up and say, yep, it works. Whatever tech debt we created, we'll take care of it later, ship it right now. On the other end, we can have the architectural astronauts, and they can talk about architecture all day long, and never actually ever write any code, never get anything out the door. And they're very expensive, these guys. So, is it worth it? So I think for us, we should go and find a middle ground so that we can write, nice code and simple. You don't spend too much time on it, and then we can have good architectures that are easy to reason about, and get our product out the door, and have something of value out there. So with clean code, there's two main areas. We want our code easy to understand, and it should also be easy to change. So looking at the execution flow should be easy to understand. You read the code, it just makes sense. Everything that our classes do, or the way they interact, should be nice and simple, and you don't have to spend a lot of time trying to figure it out. Then, when we need to change our code, things should only have one reason to change. So that single responsibility is very important. And again, just looking at your class interface should be simple, easy to understand, and it should do really what it says on the box. You don't want to say create new customer, and inside it actually goes and deletes a customer. That's just not nice. So all of these things put together is nice. It's very important. And they're sort of been summed up in 5 principles that form the solid principles. And they were popularized by Uncle Bob, or Rob Martin, in his book, Clean Code. So if you're not familiar with these principles yet, that's fine. We're going to go through them. But if you are, just sort of maybe put your hand up in the chat there and let me know what you think about it. One side effect of writing clean code is that you actually end up with a lot of code and a lot of files. So you need a way to organize this. And this is where clean architecture comes in. So clean architecture sort of gives you the ability to write the core of your application. It's independent of any other frameworks. It's all testable, highly testable. You can take the UI, let's say was originally written with React. You can swap that out and use Blazor, latest and greatest. Or you can swap from SQL Server to Cosmos DB, no problem. So the core of your application shouldn't need to change for any reason. It doesn't depend on anything external. So for instance, if you're upgrading a dependency, the core of your application shouldn't need to change. And this is all possible because the dependencies all point inwards. You can see the arrows there, nothing's pointing outwards. So any changes that you're made on the outside don't change the code in the middle. Really nice. So if you want a template for getting a clean architecture project up and running in seconds, you can check out Jason Taylor's clean architecture solution on GitHub. And just a few more rules about clean architecture and a lot more coded examples. You can check out the rules to clean architecture link at SSW. Okay, so now we know what clean code is about, what solid principles there are, and how are we now going to apply that to serverless. So I'm going to take a simple application and call this our classic example. It's just a simple app. There's a server, there's a database, and a static site. These days in Azure, we'll say it's a static web application. So the icon's slightly out of date already, but it's very much the same thing. Okay. And we've got our readers that go to the site, and we have authors that go and add new content. But as developers, we would like to imagine the worst case scenarios. So when things go wrong, and they go really wrong, it might just be your server RAM or hard drive space. Yeah, things just stop working. We don't have connectivity to the application. We can't update our site. We can't even get to the database. So we're starting to panic, and we don't really know what our user experience is going to be right now because even the static site can't access the API for any sort of dynamic information. Okay, so we go away and try and figure out what can we do to make this better. And you'll definitely run into serverless. But why would you want to go down the serverless path? Well, when a server goes down, you don't know about it. The serverless providers, Azure, AWS, GCP, they all just take care of that for you. You generally tend to spend less money with serverless because the way that it scales sort of on demand for you, you sort of get rid of that over provisioning problem or under provisioning even. So, but digging a bit deeper, why you want to use serverless? Well, they remove or abstract all that hardware issues away for you. And you just focus on your code. So it's a very simplified programming model. It even helps to simplify your DevOps because the applications are smaller. They have less dependencies. It might just have one database rather than some applications can have access to multiple databases and dependent services. So yeah, it simplifies DevOps. Like I said, it helps you with the problem of over or under provisioning your infrastructure, your resources. So you don't have a gigantic server that is only being utilized in 5% of it, or you're always running at 100% and you can never fulfill all the requests. So this consumption-based billing, you basically only pay for what you use and no more, which is really cool. And event-driven scaling. So that's really important because our application can do things like look at blob storages, react of when a file is uploaded somewhere or someone sends you a message, not just a HTTP message, but from a message bus or Signal R, for instance. So whenever those messages come in and we start getting a spike, our application can quickly scale out and take care of just running smoothly for us. Now, because the applications are smaller, they have less dependencies and, they sort of start having less coupling. So we don't have a gigantic service that, or a monolithic service that needs to know about 5 or 6 or more dependencies down the track. So everything's just loosely coupled and it's easy to test. And you can just have much better confidence once you do release your application. So looking at the serverless services available in Azure, for compute, we have Azure Functions. Logic apps, We can even run everything inside of Kubernetes as serverless container instances. Pretty cool. When it comes to data, there's Cosmos DB, even serverless SQL is now a thing, which is really cool, and storage. So, we basically can just be concerned about data. We don't have to worry about the underlying hardware at all. You just put that record there, put that file there, done, and it works for us. Another set of services I want to look at is messaging services. So we have quite a lot of them available. So Azure Service Bus, Event Hub, Event Grid, even Signal R service, they're all available and they're serverless and they just scale to whatever demand we need. I'm going to pick these three. I'm going to start with Azure Functions because they scale elastically. I want my application to quickly just spin up more instances when my application gets used heavily, and when things die down, scale back down to 0, and then I don't pay anything. It's really nice. The benefit is also that we can run Azure Function apps anywhere. So not just in Azure as functions as a service, but we can run them in containers. We can even run them on-prem. So anyway, you can run. There's no more vendor lock-in that people be concerned about. DB provides a NoSQL sort of model, but it's actually not only SQL. So there's a few other varieties that we can use from Cosmos DB, like graph databases, column-wide databases with Cassandra, and even MongoDB. So a lot of models are supported. Really nice. And it can elastically scale. So even my application can ask Cosmos DB, hey, quickly scale up because we've got a heavy operation coming in. And when you're done, scale back down. And it happens very fast. Very nice. A really cool feature that we have as well is change notification. So what this is, once you write a record or an item or a document, everything's got more than one name. When you write a document to Cosmos DB, you can actually trigger some custom Azure function code to run, which is like a side concern. It's not maybe part of your main application, but you still want to react to that event. Maybe you want to pre-cache some data or generate a separate report. And you don't want to then have to go and bake that into your main application. This is really nice. So you can take care of some other cross-cutting concerns using the change feed. And finally, with Service Bus, when it comes to sending messages, they guarantee the delivery of that message. So once it goes into the bus, it'll always be able to be read at the other end. And we can do that with different things. We can use just plain queues, or we can use topics with subscriptions and filters. And we'll look at them a little bit later. Very, very cool. So we take that classic application we saw earlier, and after a bit of playing around, these are the resources we chose, and we broke the application up into a few smaller pieces. So we're going to use Azure Service Bus to send messages and have our functions listen to a topic, and whenever a message arrives, it will trigger that function application to run and produce some sort of output. And then for our database, like I mentioned earlier, we can use the change feed. It's very handy when a record is written to the database. We can raise an event or trigger an event and run some custom code to take care of something that's not built into the main application, or even that's not part of the main domain of the application at all. So for serverless, I'll look at a very of Azure Service, but I'm excited already. How does the solid principles apply to our serverless applications? So the first one I'm going to cover is the single responsibility principle. It means that we only want to have code have one reason to change. This principle actually goes hand in hand with one further down the line, the interface segregation principle, but I'm going to cover them separately. So an example of SRP with our application is the resize images application. So if I need to change this application, it's only because I need to do something about images. It has absolutely no concern about the markdown that we process in another application. So, I don't want to make a change here and down the line something else wiggles around, and it is basically just focusing changes on one small bit of functionality. one application as it is in our case. So yeah, with random markdown, like I mentioned, if I change it, I don't want anything to change in the render images application at all. The next two principles, you can sort of combine them together and build something really nice. So the open-close principle, it means open for extension, but closed for modification. So imagine we have just version 1 of an application out, and we want to improve on that. We don't want to go and just rip out the application from production and slot the new one in. We can do that in a really nice way with Azure Functions. And LSP, or the Liskov substitution principle, is that we can take an implementation and swap it out for something that does the same thing. So like I mentioned in our example, here's just a smaller slice of that application. With the resize images again, let's say now I want to go and write version 2. It does the resizing quicker, it probably has a bit higher quality, but I don't want to have to swap the version 1 in, swap out version 1 straight away while I'm developing version 2. So I can actually deploy version 2 straight away. I can react to the same messages that version 1 gets. I can test the output, can write it to a different site or anywhere else, just to have some way of monitoring the output from that. And then once I'm happy, cool, I hook that up, I'll put its output back to production. I can turn off the messaging for version 1. Now it's gone. Version 2 is running, and it's all happens very quick and easy. Cool. Now this is the interface segregation principle. And this one for me is very important. People tend to try and write massive, great APIs, and then we end up with even monolithic serverless applications. So when you have an application, try and limit the number of endpoints or the number of features that you're trying to build into that application. There's a few basic benefits that you get. So you have less dependencies, potentially. So your application binaries are going to be smaller. And that also helps to not improve just the cold start times, which is a serverless feature, but it also helps your applications scale out quicker. So when that event-driven demand comes in and your application has to scale, in the background, of course, your application, Azure will have to provision some more VMs, copy the code from a storage account onto the VM, spin it all up, and if your application is small and starts quicker, you can react quicker. So imagine it was just a huge application. It took 20, 30, 40 seconds to boot up, connect all the databases and all things it needs. You're not going to be able to scale very quickly. It's not going to really be useful. So in our example, if we focus functionality, or again, in this case, resizing images, it can scale up really quickly and scale up quite widely. You can have many instances running to do a lot of the work very quickly and efficiently. So we can only scale out one small bit of functionality for our application, unlike the classic version where we'd have to scale out the entire application. So we don't need huge amounts of horsepower to turn Markdown code into HTML, for instance. But images, for sure, they take a lot more processing power. So this is very ideal, very nice. The last principle is the dependency inversion principle. And as it says, code towards the interface. And for a long time, I was trying to figure out, hey, how am I going to take this principle and apply this to a serverless architecture? And the keyword here is code. So that's what we do with our applications, not what the applications can do to each other. So there's no easy way for me to apply this to an architecture other than being able to actually now do it in our serverless applications. So for a long time, our serverless applications didn't have a way of doing dependency injection, which is important for clean code. Coding towards an interface that we can then go and swap out an implementation. But now we can. It's really good, and it actually helps us write really clean applications. So I'm still going to take that one as a win. Here's an example. Here is one of the service bus triggers. So it receives a message from a particular topic on a particular service instance. And what we're then doing is just serializing that message into one that we can understand. And a lot of times we use mediator or even something like any service bus, is pretty much the same thing. With the messages that can be considered as a request. And then we just use mediator to send that off. So we don't actually have endpoints that are really thick. They're very skinny, very simple to understand. And just like with classic web APIs, we have a very thin controller and a very small action. So we've injected the dependencies via the constructor for our serverless application, and it's very easy. It all fits on one screen essentially. And then that request that came in, send it through mediator, and then it gets handled here as an asynchronous request handler. And we have, again, dependency injection through the constructor. And then in the handling method, we have the incoming request object, and we can, in this case, go and download the original image, resize it, and return the output. Cool. So looking back, serverless and solid principles, we can pretty much tick each and every one of these and say, hey, cool. Now we have at least 5 good principles that we can use to reason about how to build or architect our serverless applications. We're not sort of stabbing in the dark. These are things that have been tried and tested over 30 years or so. Some of them have a long, long history. And it makes life easier. It lets us not just write simple code, but build simple architectures that are easy to understand and then make sense. Everything does exactly what it says on the box. Cool. So, okay, now we know. We can write some cool, solid applications, everything easy to understand. How do we harden our applications? Once we send it out into the wild, all sorts of things can happen. So this is where automated applications are resilient. And why do we want to do that? Well, we don't want to lose any operations. When you have a commerce site, for instance, someone clicks buy, that message that goes into the system, if something happens, server runs out of memory, restarts or whatever, we don't want to lose that operation. That's potential revenue that we're basically missing out on. So we want to make sure that we don't lose those operations. We want to keep them, even though something goes wrong in the middle. But we want to resume the operation as soon as possible. Once things come back online, we just want to keep going and not be too concerned. And this is because we do want to provide a highly available service. So when do we start panicking? Well, we always imagine natural disasters. People joke, oh, the data center is on fire, but that almost never happens anyways. Lightning strikes, almost just never happens. But what happens often is when someone accidentally restarts a service. I'm sure we've all been there, or just part of our normal CI/CD pipeline or a DevOps cycle. When you deploy your application, you have to take it offline and to swap in the new version. That just has to happen. And in that window, customers can still access your application, and it may not work. And then just transient errors. These things happen. For instance, when that classic application I showed earlier, suddenly I want to convert 50 images and my storage just can't handle it, or I need to store a whole lot of documents to the database and I'm just running out of connections. So those sort of transient errors, they do happen. Or even just when you make a configuration change to your application, often they just have to restart to be able to have that setting take effect. So all of these can actually make you panic, and we want to be able to deal with that and not actually lose any valuable operations in our application. So just looking at the setup for our basic application again, when things go wrong, we lose all connectivity, we really start panicking, we don't know how the users are experiencing the application really, they may or may not come back at all. So how do we solve this? How do we get rid of the sort of brittleness and have our applications nice and resilient? Well, one way that we can do or achieve that is to use asynchronous messaging. So this is where the Azure Service Bus type services come in. It's not the only one, but it's one I've chosen for today. It's just because HTTP requests, they suck. they have timeouts, and you can't recover from that timeout really. Once it's that operation is lost, if the user doesn't want to come back to your website to submit that order or to click that buy button, well, you've missed out. It's not going to happen. The nice thing about messages in these sort of services is that they are persisted over outage periods. So as soon as you've received that message, it's yours, and you can keep it for a long time and make sure that you can process it at some point, and then at least make sure that that buy or that sell operation goes through, and you actually still have a happy customer. And they also reduce coupling between the applications. So when we think about clean code, even there's the term new is glue. So if we couple our classes together, they're very hard to refactor and hard to change and hard to swap out behaviors, right? So when we use this sort of asynchronous messaging through a bus, then we don't need to couple services together. We literally say, hey, I'm raising an event. I'm throwing a message into the bus saying order created, and any service that's listening to that bus can pick it up and react to it. We don't know who it is. So basically we can fire and forget the messages because you've done your bit. This one service has done its bit, and it just sort of throws into the bus, and the next service can pick it up and continue its process. So it's really nice. But again, even though it's such a nice service, we have to look at which patterns to use to make them highly available. We can even actually use some highly available services already. So let's say, for instance, Cosmos DB makes it really simple. You can spin up a Cosmos instance and say, I want to run this in not just in Melbourne, but I run it in Sydney, New York, and LA. That's my customer base, and I can literally do that with 4 clicks. It's nice and simple. And you can turn on a nice feature that's going to make it even better. So it's called multi-master writes. So if we compare what that means with SQL Server is, of course, SQL Server can run across the globe in multiple regions, but you can only write back to the single master node. So if I have a customer from New York wanting to write something to the database, they have to come. That request has to go all the way down to here in Melbourne if that's where my master node is. So that's a long time to, a lot of latency for that operation to complete. But turning on multi-master writes in Cosmos, that customer in New York can write to the New York instance straight away and read whatever information from that database straight away as well. It's highly available. And Cosmos actually takes care of that replication all the way back to Australia for us. All the master nodes in each region has the same information. And then, so it means if anything happens to our Sydney or Melbourne nodes, the ones in America, they're all still functioning fine. Nothing wrong with the application. It's all good. Then for our applications, there's sort of the outbox pattern. Instead of directly sending messages right away when we need to, we can actually sort of have like a persistent store in the application just to make sure that, hey, I know these are the messages I need to send, and I'm going to work my hardest to send them as quickly as possible. So even if the application did go down halfway through sending a message, when it starts back up, it'll go, oh, I didn't finish that message. I can actually resume and send it out. So it's really valuable pattern, and it's not actually very hard to implement in your applications. And just retry patterns. So these are in the instances where, let's say I'm trying to do a select from the database and it fails. I've run out of connections for some reason. So that's like a transient error. So instead of reusing that very same connection, we can retry with a new connection until we do it like a hard fail. So these are simple. You can use Poly, which is a very popular library that we can use for .NET. And yeah, it's definitely worth implementing these patterns to make sure your app is resilient. And before you do hard fails, at least you try your best to recover. So when we look at our serverless application, when things go wrong, and they do, because nothing's perfect, and even though it's serverless, things do go wrong. But when do we start panicking? Well, as soon as the applications start coming back online, they don't all come back at the same time. It might take a little while for them all to come back. But let's say the first one comes online, that's okay because the messages are persisted in the bus and they're not removed from the bus until it's processed successfully. Excuse me. So that's really, really nice. And same with the other functions, even for Cosmos DB, when they come back online, they go, oh, there's been a number of changes since I last read the database. So, we'll just resume from that checkpoint and keep on processing. We've literally not lost anything. Again, just sort of messages now, we've got documents coming down the wire and we can process them as soon and as quick as possible. And that's just nice because eventually everything's back online. We've missed no operations and we can stop panicking. Nice and simple. So looking at Service Bus itself, we need to make this highly available. You're spinning up normally just one instance, but it's in one region, and it does. Something in a region can fail. You always have to have something available elsewhere in the world where there's no disaster, and you can always fail over to that. Hopefully, that it's not too far away. So even though it is just a little bit of distance away, it's not too far away. So you don't want to have too much latency in your application. So what we do, we take our Service Bus instance, we deploy it into 2 or more regions, and then we look at, say, an active replication pattern. And what that means is our sending application, it sends the same message to both service buses. But on the receiver end, we're not going to receive the same message twice. So this is where we have to make sure that either, if we want to process the same message twice, the second one doesn't have a negative impact or no side effects to that operation. So the term, which is one of the harder words in English to say, is idempotent, however you say it. Everyone's got their version of saying it. But or we have to then find a way to deduplicate the messages at the receiver's end. So we only process that message once. Now, not everyone I talk to has actually been able to achieve this. It's actually quite hard. Sounds simple, but it's a fair bit of effort to make this work. You have to have a store available at each application that receives a message to look up correlation IDs and all that sort of stuff. But then for how long do you keep all that information? There's a lot of complexity involved in this pattern. It works, obviously, but it's very hard to deal with. A better approach would be the active-passive replication. This is actually the recommended pattern from Microsoft as well for Service Bus, because we don't have to deal with that deduplication of our messages. And it's quite simple. We still have 2 buses. One's an active and one's a passive bus. And they're both in different regions. So we first always send messages to the active bus, and only when that send operation fails, we'll fail over to the passive one. But our receiving application listens to both as well. Just like with active, we're listening to both active and passive buses at the same time. So what that looks like, it's like this. We have our sending application on the one end, and it sends the same message to both of the buses. Our listening application receives it, but then we have to go through and deduplicate that message before we can actually handle it or process it through our application. Now, it looks simple, but that one step is sometimes very hard to implement properly. The active-passive replication looks like this. So you start with the sender application sends message 1. It goes through the bus. The listening application can receive it, process it, not a problem. Message 2 fails to send through the active bus. And, so we can actually retry that if we wanted to, try the retry patterns. But when that fails, we then send through that the very same message number 2, to the passive bus. And the listener can pick that up and just process it. So you'll receive only one message from either of the service buses. You're not going to receive the same message twice. So nice and simple, and it just works really, really well. But then how do we make our Azure Functions highly available? Well, again, we start by deploying them into multiple regions. There are multiple instances of that application are now running in Azure. But going the other way, if you look at the active-passive pattern from before, each application will have to know that there is 2 receiving applications in 2 regions. So we actually have to build a lot of logic into our applications when we want to send a request between the services, and try and fail over manually, which is quite a bit of annoying work that we need to do. So if we look at the active pattern, which actually is the recommended pattern for serverless applications, or at least something that goes over HTTPS. But you think the problem is with active is that I'm going to receive the same request twice, or more than once. And that makes me sad, because as we saw, we have to deduplicate and make sure that if we run the same operation a second time, there's no weird side effect. But there's actually a very cool service that we can use to solve this problem for us. It's Azure Front Door. And what that looks like is once we spin up Azure Front Door, we get a new public endpoint for our application, and we register all our APIs for different regions in Front Door. We can even set up some awesome routing policies if we need to. And Front Door will actually do like a near instant failover between regions for any request that comes in. And in fact, it will actually find the closest or fastest region to route to for any request that comes in. So you can see here we've got 2 sets of APIs in Australia Southeast and Australia East, and Front Door just takes care of sending the request through the right one. Now, traditionally, if we did use SQL Server as our database, we'd actually have to set up a SQL Server in both regions and then set up replication between those regions. But with Cosmos DB, we don't have to worry about that, because we can just tick a couple of features and they take care of it for us. So the scenario actually becomes really simple, nice and easy. And you don't really need a DBA or a database engineer that can set up that replication for us. But now if we go and we take the 2 patterns that we looked at for high availability, and we combine them into the whole setup here. So we have our Front Door running our applications across regions, and we have a highly available service bus set up here, and we want to follow that active-passive pattern for service bus. This is what it looks like. At first, it might be like, oh, what's all the arrows, and a bit of mind-boggling, but it actually works really nicely. So for each region, it will have its primary and passive, primary or secondary or active-passive bus, and they will actually just ping-pong or switch depending on which region it is. And it actually, at first I thought, hey, this is going to be hard to build, it might not work. Built it, and it works really nicely, and it's far easier than I thought. So definitely give this a try. So just looking at service bus messaging, sending messages. Just a couple of tips is to in your base message that you send is to include all basic information as you can. What message type it is, correlation IDs are important, so you can track that across multiple services or multiple operations. And even where it came from and whatever, anything that is valuable. So have that available in your base message. So everyone can sort of have a common way to handle this message. So in the Azure Functions, we use the service bus trigger to listen for incoming messages on a particular topic or a queue, even if you want to use that. And to send messages, we can use the topic client. Now you can also use the service bus output binding, but I find using the topic client deeper inside the application usually is a bit more convenient. If you want some code, I have a fairly big project there that you can look at for a sort of modern enterprise service bus workshop that we did a few months ago for NDC Melbourne. Brendan Richards and I did this. You can have there, just grab all the code. It's all there. It does pretty much everything that we talked about up until now. But just to give you a bit of a taste of what's in there, here is a way of sending messages. Now, to fit this on one screen, it's not the version where it does the failover to the passive one, but it will be pretty easy to implement. So we start off by making sure that any base message that comes into our message sender, we encode that to UTF-8, we serialize it as JSON, and we make sure to include the data type as the label for that message. So at the receiving end, we can actually deserialize that into a concrete object. So here's just the message reader that we would have on the receiving application. This is how we then dig into that JSON payload that comes back, and we find the message type and return then the .NET type, which we can then use for some JSON deserialization. Get the concrete object, and just like earlier, here's a service bus trigger for a request that comes in. We read that message, and if it's in our case, my base messages, I always have them as mediator requests. So I can actually use mediator to then send that through the pipeline, and eventually in the application, handle that message. And here we go. So here's a message that comes in, gets handled, and we have the original request, and just take care of it in mediator. So very nice and simple. So cool. Now we know, clean code, the solid principles, they do apply to serverless, and we know at least how to make our applications resilient with asynchronous messaging and high availability patterns. But what about scalability? Well, okay. First, I say is make sure that you know how big you want to scale your application. In Azure, you've got different ways of running your serverless application. Your Azure Function application, so you can run it as a consumption plan, which limits you to 200 instances, which is quite a lot. The premium plan, even though you've got more powerful CPUs, multiple cores, all that, you're limited to 100 instances. And if that's not enough, then you have to think about adding multiple plans, or maybe even using the consumption plan as an alternative. Definitely when you're looking at the dedicated app service plans, you can run an Azure Functions application on an app service plan, but you're limited severely into the number of instances that you can scale out to. But then if you're running Kubernetes, well, then it totally depends on a lot of things. How much hardware have you got available, and whether or not you want to use the virtual kubelets to run all those serverless containers, or Keda, to sort of scale out automatically for you and scale back down to zero. So Kubernetes, it really depends on what you have. Okay, then like I said earlier, it's very important to keep your applications small. You can definitely notice it in the startup times and the scaling times. When they have a lot of binaries to load, a lot of things to connect on startup, then it's not great. Then also, when your requests come into your application, try and make it as quick as possible. Don't try and block on an incoming request for a long time. As soon as you can return a message back to the user, you should. And a good tip just for running your Azure Function applications is that it needs a storage account for all the bindings and triggers to store information, and even invocation logs, all that, to maintain the application state. So if your app, you need to write some results to storage, if it's images or files, PDFs, anything, use a separate storage account. You don't want to negatively impact the storage that your application, the Azure function is using, or the runtime is using to make the application tick over. So storage is cheap, so why not? You can definitely have 2 storage accounts for one application. To get a little extra oomph out of your application, Azure Durable Functions are awesome. In particular, I'm just going to call out the fan out, fan in pattern. So if you have a request that comes in, and it's of the sort that you can actually split it up into multiple workloads. You can use an orchestrator and fan out all those operations to individual Azure Function activities. That's awesome because you can very easily just scale out to a couple of hundred instances and let it all run for you, and it will then collect or fan in those results for you. Or another name for this pattern is sort of the map reduce pattern. So it's nice and simple to give that a go. Then, very importantly, with your messages that come, your HTTP requests that comes into your application, turn them into service bus messages as soon as you can, right? So like I said earlier, don't try and block for too long. This means, though, your application, you sort of have to design for eventual consistency, because if you're not going to be blocking a request on a request, waiting for the result to come back and send that back to the caller, instead you send back like a TO2 accepted message and give them a way to query for the result that will be processed and made available eventually. So you can use something like Signal service, for instance, to then do push notification back to the calling app to say, hey, that job you requested, it's ready, here's the result. And then when you use Service Bus, try and use topics, because if you use queues, a queue is limited to just one consumer or one listener. If you use topics, then you can actually, each topic gets a separate queue and you have filters on them, then that lets people subscribe to it. So you can actually have multiple listeners to one queue. It's really awesome. And that lets you run a whole lot of stuff in parallel. So you can trigger multiple applications running off that one topic. And this one, I was very surprised at this. So following the sort of best practices, with your access policies in Service Bus, you want to give the application the minimum capability possible to reduce any sort of surface area for things going wrong. If an application is only going to ever be listening from a service bus, it only needs to listen rights, or if it's only a sender, it needs a sending rights. The manage rights is sort of give that just to an admin type application. But the problem is with the service bus trigger, if it doesn't have the manage capability, or manage rights, sorry, it can't peek into the service bus queue to see how long the queue is, and then it can't proactively scale out for you. So I tried this on an app recently. It's like, wow, it actually just scales a lot quicker. I get more instances spun up, and it just gets the job done a lot faster. So it's much more efficient. Surprising, some of the security conscious people might say, don't do that, but I'm sure you can convince them with the end performance results are much, much nicer. So here's what a topic would look like in Service Bus. You can have multiple filters. So you can actually say, hey, the messages that come into this topic, I only want to filter on some of them. You can actually write like SQL filters to say only messages of a particular data type or from a particular person or service I want to have, and then you make that available as a subscription. So you can have one or more apps subscribe to that and trigger on it when the message does arrive. And also now, because we scale out really widely and produce a huge amount of results, when you want to store your data, it makes absolute sense to make sure that you choose the right storage service. So, to match that high throughput. So Cosmos DB is awesome. You can provision a huge amount of throughput. It does cost a bit of money, but the cool thing is you've got auto scaling as well. So it makes that job nice and easy. So no point trying to store huge amounts of results into something that's really slow. You're actually just going to slow down your application and hurt your scalability quite a lot. So you've got a few options. Cosmos DB, Event Hub, Premium Storage, and even SQL Server itself obviously has huge performance capabilities. So yeah, just choose the right one for your application. And this sort of goes sort of best practice when you deal with connections to services. Try and reuse the connection clients. Don't manually try and spin up a connection for each Azure Functions application, because very soon your Cosmos or SQL Server, for instance, they will run out of connections, and you're going to have a lot more transient errors. and it'll just slow you down. So yeah, you go for the clients that use connection pooling and manages that whole thing for you. All right, so wrapping it up. In summary, go and use serverless over the traditional approach. It definitely makes your applications very easy to understand. They're easy to maintain and extend. They're definitely testable. Smaller bits of functionality is very easy to test. So you can have a lot of confidence once you ship your application. And definitely solid. Gives you a way to reason about your serverless architectures. You can keep things very clean, very simple, and everyone can come in and understand it. Asynchronous messaging over HTTP requests, it definitely has a lot of benefits. So you can have better resiliency, your scalability increases, and your coupling between your services actually decreases. So it has an awesome DevOps benefit there. So it's very easy to just deploy the smaller bits of functionality, and that whole coordination around DevOps is a lot simpler. And high availability for serverless is actually quite easy. Surprisingly, I thought, oh no, it's going to be a lot of work, but it's super simple. So everyone should be able to give that a go. And finally, now you can go and build some awesome Rock SOLID serverless applications. And from Azure, if you want to learn Azure for free, they make that nice and easy. There's a link, azure.com/free. And if you want to learn more about Azure, Microsoft Learn's got a massive amount of tutorials and things for you to go through and help you with training for your Azure certs as well. So it's very useful. If you join the newsletter, then you can go to that Azure Developer Swag link. And if you're very quick, you can use that code to grab some free swag. Only the 4 people from this talk will get a pack. So if you're quick on the fingers, go for it. Thank you very much. Oh, cool. Definitely open for questions. Everybody got some questions?
Audio coming through.
If there's no questions, thank you very much, everybody, for turning up. I hope you really enjoy the rest of NDC. It's been fun so far, even though it's online. It's actually really fun. Thanks, Tien. What do